Hello everyone, my name is Giang Nguyen and today I'm going to talk about our paper Manas, Mining Software Repositories to Assist AutoML. This is a joint collaboration with my labmate Muhammad Sohir Islam, Rangit Pan and my advisor Dr. Haridat Ratan. So why deep neural network? This is a phrase we see often these days. Deep neural networks are a class of machine learning algorithms that have gained significant popularity in recent years due to their remarkable success in tasks that defy traditional algorithm techniques. These days, applications of deep learning include but are not limited to internet and cloud, such as language translation, um, medicine and biology, such as drug discovery, media and entertainment, such as video search, security and defense, such as face detection, and autonomous machine, such as self-driving car. And to conclude, deep learning achieves success in many applications. However, there are still many challenges in programming deep learning. One of the challenging problems is the constructing an appropriate models architecture, which also have been shown as a frequent bug in CNN program by Islamabad. For example, here are some examples of Stack Overflow about the challenge in programming deep learning. For example, here an author asking why his simple Keras neural network isn't learning. In this question, the developer were wondering why ResNet network doesn't work as expected. And AutoML is created to solve this problem by automatically generate appropriate models for a given dataset. AutoML takes the training data as an input to automatically define a neuron network for that data. Moreover, it is able to tune the hyperparameter of the searched neural network. However, AutoML also had two limitations. First, it can be very costly. For example, neural architecture search is one of AutoML technique which generate 8 times more amount of carbon footprint than using handmade model. Second, neural architecture often produce very complex models that are hard to understand and time-consuming to train. To address this problem of AutoML, we propose a method that leverages software repository mining to improve the performance of AutoML in model complexity and training time without losing accuracy. Particularly, instead of starting from a default model, the initial model is selected from a repository of models extracted from GitHub, and the intuition being that developers solving a similar problem may have developed a better starting point compared to the default model. And we also have utilized the common patterns to transform mined models to improve the performance of the models in terms of errors, model complexity, and training time. And to initialize MANAT for neural architecture search, we mined CNN model from open source repositories. Currently, MANAT collects high quality model from GitHub. After that, model matching is applied to match the data characteristics extracted from an input dataset and the mined model to obtain good starting point. It selects the model which has the closest data characteristic with the input dataset by using model clustering approach. And in case there are too many initial models, the model filtering approach will be applied to reduce the number of models. Then the selected models are transformed by the model transformation approach based on the related state-of-the-art paper the, and the common layer API pattern of the minded model. And this transformation can increase the performance of AutoML in terms of errors, model complexity, and training speed. In order to extract CNN model and their optimizers from source code repository, we build a source code analyzers based on the control flow graph. We collect the metadata of GitHub repository by using GitHub API query. Metadata contains basic information of a repository such as authors or repository name. From the metadata, we obtain top 10,000 GitHub repositories with the most data to ensure the quality of the model. And from the minor repository, we only collect Python program. Actually, we use the control flow graph to extract complete Keras models. The control flow graph analyzes the import statements of Python programs to only collect with one import Keras API. We manually create a list of function calls used to build neural networks of Keras based on Keras documentation. Then the control flow graph examines every API call to collect the function contained in the list and their connections. The collected function represent the layer in the model. And finally, we apply some filtering criteria to remove inappropriate models, such as removing incomplete model, removing unsupported model, and removing the duplicated model. The next component of MANAT is the model matching. And model matching is a ranking system used to find good models for a certain problem by using data characteristics. Instead of using constant default models, model matching finds the suitable models to use them as default models for AutoML. Model matching includes model clustering and model filtering. And the intuition behind model matching is that two datasets have similar data characteristics can use the similar model architecture to train. Each model is created for a certain problem and each also includes the data characteristic of this dataset. Therefore, we find a suitable default model by comparing data characteristics of the mined model with the input dataset. This work we focus on image problem, so we obtain the data characteristic from dataset and model, including input size, input channel, and output channel from the image data. And the model, the data characteristic also are the same as the data characteristic of the input dataset. Actually, the input size includes the height and the width extracted from the image. The input channel represents the number of primary color in the image, and the output channel is the number of output categories of the dataset and models. From open source repository, we are able to obtain various model structure as well as their data characteristics. Combine all the model with the data characteristics together, we got the meta space. And in the meta space, we estimate the distance between input dataset to the mined model by using three selected data characteristics, which are input size, input channel, and output channel. The distance is estimated by using delta I, delta O, and delta S, like these formulas, and where I, O, W, and S are the input channel, the number of output classes, the input width, and the input height of the dataset. And similarly, IK, OK, WK, and SK are the input channel, the number of output classes, the input width, and the input height of the model K. Based on the calculated distance, we apply clustering algorithm to cluster the model into small groups, like this figure, yeah, and here. And after that, we select all the model in the closest cluster to the dataset as the new default models for the dataset. Here is the selected cluster. And if the number of default model found by model clustering approach is too large, we use model filtering to filter some model to increase the performance of MANAS, which is its neuron architecture as a graph connection, and the connection between two trainable layers represents the edges, and the channel of the outgoing trainable layers represent the width of edges between two vertices. And to filtering the model, we use Gaussian similarity to estimate the similarity between two vertices. In this formula, we have Mij is an element of the similarity matrix of a vertex Vi of a graph and vertex Vj of another graph. And we create a similarity matrix M for each pair of graphs and classify the equal matrix into the same classes. And in this work, we filter the models by only using the neural network whose graphs belong to the class having the highest number of matrices. And here is an example of two similar neural architecture. And finally, model transformation is the method that transforms the initial architectures by modify or adding layers such as like normalization layer, activation layers, and global average pooling layers, and the dropout layers to optimize AutoML in terms of speed, errors, and the number of parameters. We choose the layer to modify the default model because of two reasons. Firstly, we have found many common patterns related to this layer, and secondly, many recent studies have shown the effectiveness of the layer on increasing the performance of deep learning network. And here is an example of an original model in the left side, and here an example of the transformed model in the right side. And in this work, we aim to answer three questions. The first one is how efficient the MANAS. Second, how efficient of model transformation and optimizer modification. And last, how efficient of model matching. To evaluate the efficiency of MANAS and model matching, we compare the performance of MANAS and Auto-Keras in terms of errors, model complexity, and training speed. The following graph shows the percentage change of the result of MANAS and Auto-Keras. In other words, we have the positive value show how much MANAS outperform Auto-Keras in a certain criteria. And this graph shows the percentage change of MANAS and Auto-Keras in terms of error rate. And based on the graph, we see that MANAS outperform Auto-Keras up to 47.1% on classification problem. And this graph shows the percentage change of MANAS and Auto-Keras in terms of model complexity. And in here, model complexity represents the number of parameters of the model produced by MANAS and Auto-Keras. And and based on this graph, we see that Manas produce models with 77.8% to 98.5% fewer number of parameters than Auto-Keras, the model on classification problem. And finally, this graph show the percentage change of Manas and Auto-Keras in terms of training speed. And the training speed is estimated by taking the number of epochs divided to the training time. And based on this graph, Manas model trained from 36.4 to 641.6 faster than Auto-Keras model on the classification problem. And in this work, we also create an application study to evaluate each component of Manas, and this study includes 4 different tools. The first one is the original Manas represent for neuron architecture search supported by minded model. The second one is the transformed Manas represent neuron architecture search supported by minus model and model transformation. The third one is the Manas represents neuron architecture search supported by minded model, model transformation, and new optimizer. And the last one is the Auto-Keras represent for only neuron architecture search. Based on the application study, we have some observation. The first observation is that model transformation increase the performance of Manas in terms of errors and converse time. So as you can see in this graph, we can see the green line represent for the original model and the light blue line represent for the transformed Manas. And the second observation is that by comparing the performance of Manas and transformed Manas, we can observe that minded optimizer have Manas to reduce error rates and converse faster also. So by comparing two lines of original of transformed Manas and Manas here, we can see that Manas converse faster and also have lower errors. And the last observation is that Auto-Keras may have lower error than Manas in the first few hours. However, in the last hours, Manas often find better model than Auto-Keras. So the reason for this problem is that Auto-Keras start with very complicated model that take a lot of time to train. Therefore, the number of models either searched by Auto-Keras are small, which decrease the chance to find out good model of Auto-Keras. However, Manas starts with a simple model which trains faster. Therefore, Manas may not be off to a good start, but in the end, it still outperforms Auto-Keras. And the observation show the benefit of using simple model in neuron architecture search. And yeah, finally, we would like to thank for the supporter because this work was supported in part by US NSF grant and Facebook Probability and Programming Awards. I also would like to thank my lab members and researchers of the Laboratory of Software Design. So in conclusion, AutoML has some limitation and we have proposed a novel approach to address the limitation of NAS that leverage software repository mining. We have introduced model matching for a technique a technique for matching the problem that developer intend to solve with hand-developed model minded from repository, and model transformation, a technique for adapting the minded model for the further improving and matching value. And finally, and Auto Manas outperform Auto-Keras in terms of errors, model complexity, and training speed. Thank you a lot for attending the presentation.